Hello, everyone, and welcome to today's live broadcast, Factors Affecting the Most Profitable Way of Allocating Space Between Vegetation and Flowering Rooms Inside a Cannabis Growing Facility, presented by James Eaves, Ph.D. Professor, Université Laval. I am Kaylee Bach of LabRoots, and I'll be your moderator for today's event. We are delighted to bring you this educational web seminar presented by LabRoots. LabRoots is the leading scientific social networking website and producer of educational virtual events and webinars. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the Ask a Question box located on the far left of your screen and type your questions and hit send. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, please click on the Help Desk button located in the promotional board at the bottom center of your screen, or use the Ask a Question box to let us know that you're having a problem. Please join me in welcoming Dr. Eaves. I will now turn the presentation over to him.
Hi, Kaylee. Thanks for that introduction, and thanks for inviting me today. Like Kaylee said, I'm a professor at Laval University, and I'm also an agricultural economist. My research specialty is actually investigating ways to increase the profitability of urban farming. But a couple years ago, when the cannabis industry started really heating up in Canada and in California, I started being invited to different cannabis conferences to talk about my research. And so now I split my time between urban farming and working with cannabis producers to understand how they can use technology and processes to improve their operational efficiency. Today, I want to talk to you about what I think is a sort of underappreciated topic among both researchers and certainly among many producers, and that's the benefits or the potential benefits of optimizing space within an indoor facility. In Canada, the law requires that growers grow either in warehouses or in greenhouses. And within that constraint, that creates an opportunity to increase yields by better managing how you use that space for different phases of the plant's development. And just to give you some context about how important this is, given a price of $7 a gram, which is about the average price in Canada right now, when a grower doesn't optimize space, and they can lose up to $11,000 a day, and that's an estimate for a small grower. So this is potentially a really big problem or a really big opportunity, depending on the way you look at it. I like to look at it as an opportunity because what I think it does is that it gives the grower an opportunity to manage their growing strategy and the methods they use to best utilize or create a space that maximizes their revenues per unit of space given their business strategy. This can be a really complex sort of mathematical problem. Not very complex, but it can be a little heavy to present in a presentation. So what I'm really going to try to do today is I'm going to use very simple mathematics to try to give you a strong intuition into why and how space allocation is important in the context of growing cannabis indoors. In order to do that, I have to give you a quick introduction into the process of growing cannabis, the different stages of growth, for those who aren't familiar with that process. Then I'll use a very simple example, about the simplest I could find or come up with, to show you how changes in allocation of space during the harvest cycle impact the grower's yields per unit of space. Okay. At the end of the process, I'll tell you how grower-specific, or excuse me, end of the presentation, I'll tell you how grower-specific factors impact that sort of optimization problem, and then I'll conclude. So the most common way to start growing is to use clones, right? That gives the grower the ability to control both pests and the quality of their product. And probably the easiest and the most common way of cloning is just using cuttings. And what I mean by that is that the grower will take a plant that they really like, that they feel really comfortable with, and that's what they call it their mother plant, and they'll cut off small branches. And then they'll put that small branch into some sort of medium, maybe with hormones, maybe with not, without hormones, until the branch starts growing roots at the bottom of the branch. And that process takes about 7 to 10 days. And during that process, the plant's being exposed to slightly less intensive light for at least 14 hours a day. And once the roots start circling at the bottom of the pot, then the plant will be transplanted into a larger pot. And at the point where it's transplanted, the plant is typically around 8 inches high. The next phase is called the growth or vegetation phase, or sometimes a phase, or just a veg phase. And this is when the plant really starts, the growth process really starts picking up speed. Is when the plant is sucking up all types of nutrients, especially nitrogen, in order to build a richer leaf structure and stronger branches and trunk, so that eventually the plant can can grow healthy buds and support those buds or flowers. During this time, the plant's put under more intense light for at least 16 hours a day, up to 24 hours a day. And this period lasts for about between 1 and 8 weeks, depending on genetics and the grower's kind of growing strategy. The final phase is what we call the flowering or the bloom phase. This is when the grower reduces the light cycle to 12 hours on, 12 hours off. What it does, that light cycle triggers response in the plant. It simulates basically fall, the days getting shorter, and triggers a response to the plant that causes it to start creating flowers, to start creating buds. And that process typically lasts longer than the vegetation process. It lasts about 6 to 10 weeks. And during this process, right after the lighting period is switched, the plant has something that's called a growth spurt, right, or a stretch. The plant can grow significantly, really rapidly, just within the first few weeks after switching to the flowering cycle. And by the time the flowering cycle is finished, the plant can be up to 3 times larger in volume than at the end of the vegetation cycle. 3 times is a little bit on the extreme end, but certainly it's imaginable. And I want to use kind of an extreme example for the examples are going to follow. Okay. So just what I want you to take away from this is that the vegetation period is typically shorter than the flowering period. Okay. And what we see in the industry is that the vegetation period is the ratio of the vegetation time to flowering time is getting shorter. And I'll kind of give you some insights into why later on the presentation. The second thing that's important to understand at this point and to remember is that the flowering plant is much larger than the vegging plant. It takes up more space. And the reason I want you to remember those 2 points is those are going to be the 2 basic factors that you need to consider in the examples that follow, explaining how growers optimize space between vegging plants and flowering plants. Okay. Okay, so what I'm going to do now is I'm going to move to the example, and the objective of this example is to show how changes in size or differences in size and differences in the duration of time between those two phases actually create an opportunity to increase average yields per day by changing the way we allocate space between flowers that are in the vegetation phase and flowers that are in their flowering phase. Okay, so we're going to start with a really simple example. And this is actually, it's a simple example, but it's actually a common example for small growers. So there's one, or even, I shouldn't just say small growers, often new growers also. I see a lot of architectural plans for growers, and very often those architectural plans will show a space or an architectural design where the same room is being used for both vegging plants and flowering plants. Okay. So there's one room, and we're going to assume that the vegetation period lasts 4 weeks. Okay? And I'm going to use this in the table that follows. I'm going to use V as a symbol indicating that a room is being used for vegging plants. And the flowering period lasts 8 weeks. And I'll use a simple F to indicate that phase, indicate that a room is being used for flowering. The room can hold up to 500 meters square of flowering plants. In other words, at the maximum size, at the plant's maximum size, given a room can hold 500 meters squares of those plants. Okay. So here we see, I kind of made a simple table, and it shows 24 weeks of growth, right? So the top row shows the week. The second row shows the cycle that the room is being used for. In other words, you see that for the first 4 weeks, the room is being used for vegetation. And then at the end of week 4, the grower switches the light cycle from, say, 18 hours on and 6 hours off to 12 hours on, 12 hours off, representing or simulating fall conditions. So the plant switches into a flowering cycle. Okay? And you see that flowering cycle lasts an additional 8 weeks. At the end of 8 weeks, there's a harvest of 500,000 grams, because I think what I didn't mention here somehow is that in the previous slide, did I not mention that? Yeah, sorry, I did. That each meter square produces 1,000 grams of flour. Okay. So every meter squared of our facility produces 1,000 grams of flour, of dry flour. Okay. And so at the end of the 12-week period, we have 500,000, a yield of 500,000 grams. Okay. And then we start the vegging cycle again. I think actually I made a little error here. As you can see, this actually should be the vegging cycle starts again for 4 weeks and then switches to a flowering cycle. And then at the end of the second flowering cycle, we have another 500,000 grams produced. Okay, so you see. Okay, so what we see is that every 12 weeks, the facility produces 500,000 grams of dry flour. And if we divide that 500,000 grams by the number of days, we see that on average, the facility is growing 5,952 grams per day. Okay. So next, what I want to show you is that, well, actually, let me show you, demonstrate here. You can kind of get a sense that this facility is underutilizing space, because you imagine they're both, this room here that's being used for vegetation in week 1 is the same room that's being used in week 5, right? But the flowers that are growing during week 1 are much smaller than the flowers that are growing, or the plants that are growing during the second phase, the flowering phase. So you can imagine there's a lot of space that's just not being used, right? And so what we want to do is find a way to reduce that underutilization. Okay, and so what you'll see is the way we can reduce it is basically by creating more rooms. Okay, so what we're gonna do now is we're gonna have a 2-room example. Okay. In this example, we're gonna take the 500 meters square of space, and we're gonna split it between 2 rooms. We're gonna use 1 room for vegetation, for vegging the flowers, and then after that vegetation cycle is done, we're gonna move those flowers into, or we move those plants, excuse me, into the flowering room, okay? And so that space, this is just so I can actually, I'm gonna use some simple math, and the only reason I'm doing it is just so I can actually show you some numbers to show you the actual increase in production. So that space, that's 500 meters squared, is gonna be separated between 2 rooms, a flowering room and a vegetation room. The flowering room has to be larger than the vegetation room. Okay, so we don't want to waste any space. So we're going to use the minimum amount of space we need for vegetation, right? And we're going to grow those smaller plants. Then we're going to move them into another room where they're going to grow larger. And we want to, again, use the minimum amount of space we need to grow the flowering plants while using the entire space we have, right? So the flowering plants are going to be some factor larger than the vegging plants. And in this example, we're going to assume that a flowering plant at its maximum size is going to be 3 times larger in volume than a vegging plant at its maximum size. So we can rewrite this equation here as the size of the room is split between the flowering room, which is A times the vegging room, plus the size of the vegging room. So then we can do a simple algebra where we solve for the size of the vegging room, and we see the vegging room is equal to the total size of the space, 500 meters squared, divided by 1 plus A, or 4. And so that we're going to devote 125 meters squared to the vegging room. And the rest of the space is going to be devoted to the flowering room. Okay. So this is what that kind of room looks like using the same Excel spreadsheet or table. So again, the weeks are on the top, and on the first we see, and this is the cycle in the first room, and we see that in the first room, the first 4 weeks are used for vegging. All right, then we move those plants into a flowering room, and those flowers grow, right? And then we start, and what we've done is we immediately start another vegging cycle, and that goes for 4 weeks. And then we grow 400, and at the end of the 12 weeks, same 12 weeks, we have 375,000 grams produced. Okay. I actually made another error here. I'm really apologize. This whole thing right here, just to be clear, these should be V's also. In other words, just to be clear, it's like right after the last vegging period, when we move the plants into the flowering room, we immediately start another vegging period, okay, in here. Okay. And then when we move the plants, when we actually harvest the 375,000 grams, we've already started another vegging period. So the vegging room is constantly being used, right? But what you see is what happens by splitting the rooms this way is that we've reduced the size of the harvest. Like you remember before, was 500,000 grams meters, 500,000 grams produced total. Now it's only 375,000. But what happens is after the first harvest, the harvest cycle reduces from 12 weeks to 8 weeks, right? Because after the first, because again, we're right after we take we move the plants into the from veg to flowering, we can immediately start another veg cycle while these plants are into flowering in the flowering room. And once they're done, we don't have to wait another 4 weeks. We have the plants have already, the vegging period is already done, and we just reload the flowering room, okay? And what that ends up doing is that increases our yield from approximately 5,900 grams per day to 6,696 grams per day. And that's a 13% increase, right? Just by reallocating space. Okay. So next is, okay, well, what about a 3-room case, right? What if we devote we break up the space even further? Instead of having just one flowering room, we have 2 flowering rooms. Okay? So now we have the total space is split up between these 2 flowering rooms, each of equal size, each 3 times larger than the veg room. Okay. So when we go again and resolve this equation, we have the equation changes slightly, the ratio changes slightly. And now our vegging room shrinks even further from approximately 125 meters squared to 71.4 meters squared. And the flowering rooms, now the flowering room is approximately 214 meters squared. Okay. And so now we have a new table, and we see that the vegging room, right, once one cycle's done, we feed a vegging room. Once the first veg cycle's done, we feed the flowering room. We immediately start another veg cycle. Okay. Once that cycle's done, we feed the second room, right? And then when the first room, flowering room, reaches maturity, we're all ready to load it again with the product from the vegging room. And you see that now the space is much more highly utilized, right? Again, you see the same sort of dynamic. You see that, the first harvest, which still takes 12 weeks, is now less than half the 1-room case, right? But the time to receive that is dropped from 12 weeks, which is the case for the 1-week case, to 4 weeks, right? So we have a much shorter harvest cycle after the first harvest, right? So you can think of this loss in the first harvest that went from 500 in the 1-room case to 214 in the 3-room case as sort of an investment. Like you give up, 256,000 grams for your first harvest is the investment you make in order to reduce the harvest cycle from 12 weeks to 4 weeks. Okay. And so that increases the grams per day, the average grams per day, from 5,960 approximately from the 1-room case to over 7,600 grams per day, or a 29% increase, right? So we're using exactly the same space, but we've increased the yield by 29%. And given the prices of cannabis, that's a tremendous amount of money for even a small farmer. Okay. So the takeaway here is that what we see is the ratio of the size of a mature flowering plant to the size of a vegging plant determines the sizes of the rooms, right? The relative sizes of the rooms. And then the vegging time, the amount of time it takes the plants to finish their vegging cycle compared to the amount of time it takes the plants to finish the bloom cycle determines the number of rooms. Okay, and the reason I just want to emphasize that is that what we're going to see in the next part of this presentation is that these two factors change with all these other farmer-specific characteristics, like things that are under the farmer's control, right? I'm going to talk about individual ones in a second, but I just want to have you keep in mind that those two things are basically driving this result, driving how much you can increase your yield by optimizing your space allocation is impacted by all these factors that change depending on where you're growing, what your strategy is, who your customers are, things, again, that are under the farmer's control, so that the farmer can actually manipulate those things to try to maximize the benefits they get from optimizing space. Okay, oops, excuse me. Let me skip something. That's here it is. Okay. So the first thing is, take example. In the last example, we used kind of an extreme example where the flowering plant at peak size was 3 times larger than the vegging plant at peak size. If we assume that instead the flowering plant is only 1.5 times the size of the vegging plant at its peak, then the increase in output per unit of space per day decreases from 29% to just 12.5%. So in other words, that is like that the relative sizes of plants is a really important factor in determining how much you can gain from optimizing space. Okay. Lots of things impact the relative sizes or the relative size of a plant at its veg stage versus its bloom or flower stage. One of the most important are just genetics. Right? Plants that have evolved near the equator, closer to the equator, which where we commonly refer to them as sativa strands or sativa genetics, are much larger at maturity and have much longer flowering periods compared to plants that evolved in northern regions, more northern regions. You can imagine kind of why, because plants that are down towards the equator, it's much warmer. The sun is basically out, 12 hours a day, all day long, and it's in that cycle never changes. And so the plant can spend more time building mass, and that increases the likelihood of propagation, right? Also, because it's warmer, the plant likes to get higher, so and be a little less densely, its foliage will be less dense because it's trying to get to more air movement that keeps its buds cooler, right? But the point is, what you see is a much bigger growth spurt with sativa varieties, or varieties that evolved in the equator, than varieties like the indica that evolved in more northern regions. These indicas, they are much shorter, right? They have much shorter flowering periods because just the summer is shorter. And so their growth spurts are smaller. So the variation size between the max size of a vegging indica plant and the max size of a flowering indica plant, that ratio is just smaller, right? That's one of the reasons growers really like indicas. They like to grow indicas indoors because they just take less space, and they have shorter, and they can have more harvests per year because of the flowering cycle is shorter. Another thing that's important is spectrum, right? It's light spectrum. Remember, I'm primarily talking about indoor growing here, greenhouse or growing in warehouses, but this is obviously also true for the sun. You just have less control of it. But what we find is that the spectrum and intensity of lights has an impact on the growth spurt. Will have an impact on, again, the relative size of the flowering plant to the vegging plant. For instance, low DLI, and DLI stands for daily light integral. It's the amount of the total number of photons that the plant is receiving over a 24-hour period. If plant's not getting enough light, what it'll do is the plant will have this, it will think that it's being shaded somehow, and it will have a growth spurt. It'll grow. It'll induce the plant to stretch, right? That tends to make it, again, the final plant much longer than the plant at its vegging stage. It also has some detrimental impacts on the quality of the plant. But I won't get into that here just because we're talking about space allocation. But the point is, if you're not using enough light, you're going to cause it can cause a stretching, and that's going to have an impact on how you allocate space. Another thing is just the spectrum. Blue light reduces stretching, right? More red light tends to increase stretching. And again, it's related to how the plant has evolved to respond to sunlight. And in the fall, you'll see more, the sun starts speaking, the spectrum starts becoming less blue and more red, which again, which signals to the plant, oh, it's fall, I need to start my reproduction cycle. And so it induces growth spurts. Okay. But again, the point is, because we're using artificial lights, like here I have two spectrums. This is a typical spectrum from high pressure sodium light, which is a very popular, though it's becoming less popular, light used in controlled environments. And this is an LED spectrum. And so you see that the grower, their choices in light is going to impact intensity and spectrum, and that's going to impact how the plants, how growth spurts are the size of growth spurts inside these facilities. Another factor that's important is something called thermal period, and that's just a difference between the daytime and nighttime temperatures, or in an indoor environment, the difference between the temperature when the lights are off and when the lights are on. So what we know is that as that difference becomes greater, plants, that difference will induce stretching. It will induce plants to grow faster during the flowering period. And the reason is intuitive, is because during the fall, when the fall approaches, that difference in the real world in nature expands, and it signals to the plant to begin its flowering process and stretching process. And what we found is that when we reduce that difference, we can significantly reduce the amount of stretching that occurs, enabling growers to better manage their space. And of course, another thing is just a level of temperature. You can increase the level of temperature and increase the rate of growth. Like I'm doing an experiment right now with a company, or I'm setting up an experiment right now with a company where we're trying to reduce the total harvest time by a few days by increasing the temperature of rooms by a few degrees. So again, just the takeaways is that by controlling temperature, we can control those differences between the size of vegging plants and size of flowering plants. Another important factor is nutrients. At different cycles, at different periods, when the plant's a seedling, when the plant's in a veg phase, when plant's in a flowering phase, different types of nutrients will induce stretching or induce more growth. For instance, by adding more phosphorus in the flowering phase, that will increase that stretching, right? Or vice versa, you can reduce the phosphorus to try to reduce the stretching that occurs during flowering. This is an interesting one because of some trends we see in the industry right now. And what we see in the industry is something called a single cola sea of green. And what growers are doing is that they're just growing, they're vegging their plants for 1 week. And then they're immediately switching it to flowering for about 7 weeks. So they have about an 8-week growth cycle. And they pack the plants together, right? So they're really trying to maximize the amount of dollars created per unit of space. And that's interesting because when we pack plants together, the leaves from one plant create shade on the leaves of another plant. And it changes the spectrum of light that's hitting the leaves of the shaded plants, which triggers this mechanism in the plant in what we call shade avoidance syndrome. So the plants tend to realize that they're competing with other plants and then start racing towards the light, right? And so so the takeaway is your spacing between plants will have an impact on how much they grow, all right? That stretching we're talking about, that impacts your optimization space. Okay. So now, like I said, so I don't have solid data on, I want to emphasize that my data on how facilities are managing space is very anecdotal at this point, because it's hard to visit facilities. A lot of people aren't, there's just to visit a facility, you need security clearance, you have to know the growers. But we have managed to visit about nine facilities. And it's clear that 3 of them are thinking really hard about space optimization. Whereas the rest, it appears that they're not, right? Or they're not thinking about it very carefully. Like I said, just appears that way from talking to them and looking at how they've set up their rooms. And as I said in the beginning of the case, nearly all of the architectural plans that we see from new growers don't seem to be accounting for increases in production that can happen by improving the way they allocate space between flower and vegging rooms. So the question is, why, right? Are people ignorant about this? Do they not have time to think about it, or are we missing something, right? But from talking to growers and thinking about this problem, we've definitely realized that there are many other factors that impact the optimization space, right? This model becomes much more complicated. For instance, one of the most important is just the time needed to manage additional rooms, right? Every time I start a new room, right, or I add a new room, I create labor needs. I create a need for time to move plants from the vegging room to a flowering room. And that's costly. And I don't mean costly in terms of the dollar cost of labor. I mean costly because say it takes 3 days to break down a room, the vegging room, and move the plants in the flowering room and then restock the vegging room. Those 3 days are extremely valuable when something's selling for $7 a gram, right? So in other words, that time becomes incredibly important because it reduces the number of harvests I have a year, right? So to give you an example, here it is. I have the example. Excuse me. If it takes 3 days to break down the vegging room and restock the flowering room, if we add those 3 days to that model we did, the 3-room case, so we say, okay, the harvest period takes 3 extra days. That reduces the benefits of moving from 1 room to 3 rooms from 29% to just 16%. And if we go further and say, okay, now the plant's only 1.5 times as large, the flowering plant's only 1.5 times as large as a vegging plant, and it takes 3 days to break down a room, that reduces the benefits from 29% to just 1.6%. So it's extremely sensitive to time, right? And that 3 days to break down a room is about the amount of time it takes to break down a medium-sized room. Okay. Other factors, it's just costly to build new rooms. Like in Canada, there's so much regulation around how you build rooms. Just adding a door is $3,000, right? And then you have to add different types of security measures. And so it can be extremely expensive to build, to basically add another wall and another doorway. Also, there's regulations about how the room is designed. You have to have 2 aisles, you have to have 2 exits. And so every time you add a new room, you basically lose 5 feet in that room because you have to have an additional aisle that's large enough for a wheelchair to turn around in. And so basically each time you add a new room, you're reducing the total amount of space you have for growing in your facility. Okay. There's issues about managing contamination, right? When I'm moving plants around from room to room, I might be more likely to also move pests and diseases, right? On the other side, if I'm just using one gigantic room, if one plant becomes infected with something, it's much more likely that it'll spread to lots of plants versus the other case where I just have one room and I have many rooms. And if I have a contamination in one of those rooms, it's much easier to control. Okay. And there are other reasons also. One very likely reason is just that this market is growing so fast right now, and the revenues are so high associated with the revenue you get for getting plants out the door, that there's just not a very strong incentive right now to think about little details like space optimization. I mean, maybe they optimize their space, but it's not like they're collecting data and thinking about what genetics they're using and what light spectrum they're using and how that's going to impact the right allocation of space. It's more like, it's $7 a gram today. 6 months from now, it might be $5 a gram. Let's just produce, and it's not like a lettuce farmer who has their margins are so thin, they have to think about every way they can possibly add another gram per unit of space. Right, so there's weakened incentives because the market's so hot right now, and also these are new growers. A lot of people are getting sucked into this market that actually don't have very strong agricultural backgrounds, and so they might not be sufficiently data oriented. Some are very sophisticated, but many aren't. But eventually they will be, because as prices come down, the only thing that's going to matter is operational efficiency. So basically, what I wanted to show you in this presentation was to give you some intuition about the opportunity that exists here, right? There's a lot of efficiency gains that can be made from optimizing space and understanding how all these different factors impact space optimization. Let me give you an example. Like I said, certain growers, they prefer certain genetics. There's thousands of different varieties of cannabis right now, and many of them behave very differently in terms of the way they grow and the client or customer experience they create. And as my customers change, right, and I want to provide variety, right? Either my customers are changing, so I want to provide new types of product, or my customers don't always want to buy the same type of product. They want to have choice. And so that means that my plants are going to change, and that means that those factors we discussed about how much a plant grows after flowering, or how long the veg cycle is relative to the flowering cycle, are going to change with genetics, are going to change with my customers. Yet my facility doesn't change, right? Even though that change implies that the way I optimize space should change, my facility doesn't. There's solid walls usually. The trays are connected to the floor. It's hard to move things around. And so one really interesting research opportunity and just practical opportunity for the industry is how can we build facilities that are more capable of taking advantage of this opportunity, the space optimization opportunity that's created by both the plant and the grower's growing strategy that changes all the time. Okay, well, thank you very much, and I look forward to your questions.
Thank you, Dr. Eaves, for that informative presentation. Dr. Eaves will be answering questions via email. I would also like to thank LabRoots for making today's educational webcast possible. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through June 29th, 2018. You will receive an email from LabRoots letting you know when this webcast will be available for replay. Please share the announcement with your colleagues who may have missed today's live event. That's all for now. Thank you for joining us. We hope to see you again soon. Goodbye.